Okay, so now we're on the back of page 3. We got back of page 3 and page 4 to go. All right. All right, so we have some more placing these in order, and why did we place them in that order? So we're going from greatest to least electronegativity, and we have potassium, selenium, and zinc. So zinc's here, selenium's here, and potassium's here. Well, I know the trend points up and to the right, so I'm going to say, so from greatest to least, so we have selenium is the greatest out of those three. And then we have zinc, and then we have potassium. Because I just went from right to left. So selenium was the highest, zinc was the second highest, and potassium was the lowest, right? So that's in order from greatest to least. Why did I place them in that order? Well, it's harder to remove things for a given number of shells, and we can all agree that all of these things have 4 shells. Potassium, zinc, and selenium all have 4 shells. But what do they have different? Potassium has 19 protons, so it's not pulling very hard to try and remove an electron from anything. Zinc has 30 protons, well, which is getting to be a higher effective nuclear charge, and selenium has 34. So which one's going to pull harder on an electron that it sees floating by? Well, selenium is. That's why. Because of nuclear charge. Nuclear charge. Charge. More or less protons, right? Protons are what are affecting everything there. For a given number of shells, more protons are going to pull electrons harder. It's also going to be harder to pull an electron off of an element that has the same number of shells but has more protons, okay? From least to greatest electronegativity, polonium and sulfur. So polonium is here, sulfur is here. From least to greatest, it's polonium, then sulfur. PO and then S. Why'd you place them in this order? Polonium has lots of shells, shielding. So it's not going to pull very hard through 6 shells of electrons. No matter how many protons it has, it's going to have a lot of shielding. Whereas sulfur only has 3 shells, right? 3 shells. And it's easier for these 16 protons to pull through 3 shells than it is for these 84 protons to pull through 6 shells full of electrons, right? That's why. Okay, place the following in order from greatest to least electronegativity. Greatest to least. All right, so we have carbon, calcium, and chlorine. I can do this without even looking at the periodic table. They go chlorine, and then they go carbon, and then they go calcium. How do we know? Chlorine is here, carbon is here, calcium is here. So from right to left, I think they meant to choose like silicone, something in the same, so that you didn't have to make a judgment call. But basically, we know if you're not with a teacher, coach, or club sponsor, then you blah 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 blah. And she's gonna say it again. Do you believe this? Can you believe this? Okay, so yeah, chlorine, carbon, calcium. Chlorine obviously going to have the highest because it's right by fluorine, which is the absolute peak of electronegativity. Carbon's going to have less. I realize it has less shells, but it's more steps to the left. And then calcium has the same number of shells, but just a lot less protons. So that's why. That's why I placed them in that order. I placed them in that order because I know where the trend goes, basically, right? In graph A below, which periodic trend does this best represent? So increases, so up and to the right, but it's not excluding noble gases, so it's got to be ionization energy. In graph B below, which periodic trend does it best represent? So it's down and to the left. There's only one trend down and to the left. That's atomic radius. Graph showing the ionization energies for the first 85 elements. Okay, so what would the ionization energy be for barium? So I got to find barium on this chart. And the way you do it is I count dots. I don't look at these atomic numbers down the bottom. It's just too you know, there's too many areas in there. Barium is 56, so I know it's going to be somewhere right here, right? It's going to be somewhere right here. Barium is right next to cesium. So if this is cesium, the very next dot going to the right, that's barium. All right, and then I'm going to measure out and see, oh, let's see what we see. Something like, I don't know. So around 500, right? 500 kilojoules per mole. And then chlorine. So chlorine is atomic number 17. So I'm going to look right here. Oh, is it this guy? Yeah, it's that guy right there. Okay, so argon, chlorine. If I go back one, I should be right on that dot. So argon, back one dot, chlorine. Yep, that's chlorine. And I'm going to say that it's 1350. Can't be wrong on this one, right? I'm going to say it's 1350. We should look it up just as an exercise to see what, but anyway, doesn't matter. Okay, which element is more reactive, and explain why? Rubidium or lithium? Here's rubidium, here's lithium. Well, everything is shells or protons, and in this case, it's straight up shells. Rubidium has a lot more shells and one valence electron. So the pull on the center, that one valence electron is further away, so it's not holding it in as tight, so it's just going to be easier to pluck off. So rubidium is going to be easier. It's actually one of the most, and why is because it has more shells. More shells, shielding, which means it's going to give away. More shells, shielding. Let's just put a complete answer here. Let's just do this for you. More shells, shielding the nuclear charge. Therefore, less ionization energy. And that's it, man. More shells shielding nuclear charge, therefore less ionization energy. Therefore, it tends to almost give away that electron. Therefore, that's why it's reactive. Okay, oh, page 4, we're there. We're almost to the end of this thing. What is the trend for reactivity in metals? It is down to the left towards francium. Francium, let's spell it right. Act like you have a chemistry degree. What element is the most reactive element in the periodic table? Ooh, but we did not talk about that. So we need to talk about whether fluorine or francium is more reactive and why. So let's discuss each case. Fluorine is most reactive because it's trying to pick up electrons, right? And francium, so remember, fluorine, high electronegativity, is pulling really hard to pick up electrons, right? Francium, because it's trying to get rid of one of the electrons. So really, we just have to decide between these two, which one is more reactive. Well, I'm going to tell you right now, the fact that this only has 2 shells and a large nuclear charge makes this fluorine the most reactive thing on the periodic table. It's trying so hard to pull electrons off of, oh my God, I'm going to get panned for that one. I know. I should just reshoot the whole thing. Fluorine, yes. Let's spell it right. How about? It's the end of the day, and you know how I get at the end of the day. Okay, so it's fluorine. How does an element's position on the table determine reactivity? Well, as long as you know the trends, you know the 2 trends, and the trends. So we know that if we draw our stair step, we know the trend, not including, let's just close that out a little more. Not including noble gases. We know that nonmetals, it goes up to the right, and metals, it goes down to the left. And basically, its position is how close is it to getting a full valence. The closer it is, and the closer it is, and the ease with which it can get to that full valence determines its reactivity. So fluorine it has 7 valence electrons. It only has 2 shells. It's pulling very hard. It's trying very hard to have a full valence, and it's going to try harder than all of this stuff. Therefore, it's more reactive. Francium has lots of shells and not very much nuclear charge for its 7 shells. Therefore, it's really trying to get rid of an electron, so that's why the trends are in those 2 corners. Okay, which types of ions are usually smaller than their parent? Anions. No. What am I doing? Good Lord. Cations. Cations are smaller than their parent. Why? Because they lost electrons. Which types are usually larger? Anions. Oh my God, you can tell it's the end of the day. Because they gain electrons, and anything that gains electrons is going to get bigger. Anything that loses electrons is going to get smaller. Circle the one in each pair that has the larger radius. Well, now saying that, I just know that everything that's negative is going to be bigger, and everything that's neutral is going to be bigger than its positive. So that's quick. And basically, you can tell why. Iodine has 7 valence electrons. 4, 5, 6, 7. If I add another electron, the repulsion of those electrons forces it out and makes it slightly bigger. That's why. So if I add electrons, it gets bigger. Whereas if I remove electrons, usually you're removing electrons and it's falling back to an inner shell, so it's getting smaller. Okay, for each of the following elements, give the charge of its ion and circle whether the ion is larger or smaller. Well, this is going to be quick and easy. Aluminum is right here. The charge it usually takes on in its ionic state is its oxidation number. So it is plus 3, larger or smaller than the parent atom? Smaller. Sodium is plus 1. And it's smaller. Fluorine is minus 1, and it's larger. Sulfur is minus 2, and it's larger. Nitrogen is minus 3, and it's larger. Strontium is plus 2, and it's smaller. And that's it, guys. So good luck on your test whenever you may be taking it. I hope this helped out a little bit. If you have any questions, you know where my remind is. All right, see ya.